Hello everybody, welcome to the 4.6 concept video where we're going to be talking about a new integration method called integration by parts. And this is along the same lines of what we were talking about in 4.5. I'm going to start now looking at more complex functions and how do I find the antiderivatives of these functions? Because that's how I integrate, is I integrate by finding antiderivatives. In 4.5, we looked at composition of functions, and we learned about the strategy called integration by substitution. Well, in this section, we're going to look at how do I find the integral of the product of two functions. Well, if I were to take the derivative of this, I would have to use the product rule, which complicates things, right? It makes my derivative much more complex than my starting function. And for that reason, there's no nice, easy integration rule for a situation like this. Instead, we have to use an integration method called integration by parts. And for us to understand this method, first of all, we need to understand the product rule. So let's review the product rule. If I have two functions, I'm going to use u and v as my two functions. If I have two functions, u and v, multiplied together, and I take the derivative of these functions, what do I get? Well, I get u times the derivative of v, so dv over dx, plus, and then I just switch it, v times the derivative of u. Well, what integration by parts is it uses the same derivative formula. It uses this product rule and just sticks an integral next to it all. This might seem complicated, but what happens when I integrate a derivative? Remember, they're opposites, so they end up just canceling out. So I'm left with u times v equals, and then on this side, remember, I have an integration property of addition, so I can separate this into two separate integrals. Notice the dx's cancel, and I'm left with this beauty right here. U times v is equal to the integral of u times dv plus the integral of v times du. And the way integration by parts is used is by solving for one of the integrals here, solving for one of the definite integrals. And so we like to solve for the u one. So u times dv is equal to u times v minus the integral of v times du. And this right here is integration by parts. If you ever look this up on the internet, this is what it'll show you, is this formula right here. And you might look at this and think, wait, how is this actually helping? It's taking an integral and making it longer, and I still have an integral, right? I still have an integral right there. So how is this even helping? And that's true. That's something to understand about integration by parts, is it's not something that directly solves for the antiderivative. All it does is it rearranges the integral. It allows me to rewrite the integral in hopefully a way that's simpler, in a way that I can actually find the antiderivative. So what do we notice here? So here I've switched everything in terms of u and v. And the thing to keep in mind with u and v is notice what I'm going to end up doing with u as I move forward. If I'm starting with a function u, in order to rewrite it using integration by parts, I need to know the derivative of u. We call u the differential function. Why? Because you're going to take the derivative of u. But then my other piece is this dv piece. dv represents a function. It represents a function, but instead of being a differential function, if I start with dv and end up needing to figure out what v is, that means I'm actually integrating it. I'm finding the antiderivative. So this is what we call the integrable function. Because with this function, I'm doing the opposite. I'm taking the integral of it. So when you use integration by parts, if you have two functions, the first thing you have to do is you have to classify one of them as your differential function and classify the other one as your integrable function. Your differentiable function, you will be taking the derivative of. Your integrable function, you will be taking the integral of. You'll be taking the antiderivative of. So let's look at a quick example of how this works. I've got the integral of x times e to the x dx. Hopefully you can see how this function has this function is the product of two different functions. Once again, there's no easy antiderivative rule if I have two functions being multiplied by each other. I have to use this process of integration by parts. So first thing I need to do is I need to figure out which one's going to be my differentiable function and which one is going to be my integrable function. The dx, this dx will go with the integrable function. Well, let's consider both options. Let's take a look at each of these pieces. Consider x. Once again, I can either choose this as my differentiable function or my integral function. And what's nice about x is I know how to find the derivative of x, and I know how to find the antiderivative of x. The derivative of x is just 1. The antiderivative of x is x squared over 2. Now what's interesting here is one of these is far more simple than the other. The derivative of x is way simpler than the antiderivative of x. So it might make sense to choose x as my differentiable function because the derivative is so much simpler. But let's take a look at e to the x just to make sure. Do I know the derivative of e to the x? I absolutely do. The derivative is just e to the x. Well, what about the antiderivative of x? The antiderivative of e to the x is also just e to the x. So with this function, the derivative and the antiderivative were exactly the same. The antiderivative didn't complicate my function at all. So for this one, it doesn't matter which one I choose it as. I could choose it as the differentiable function, or I could choose it as the differentiable function. So based off of this, we really want to pick x as my differentiable function. Why? Because the derivative is so much simpler. And if I pick e to the x as my differentiable, or my integrable function, the antiderivative doesn't get that much more complicated. So now that we've made these choices, first of all, I need to know what du is equal to. Du just represents the derivative of u, so it's just 1 times dx. And I need to know what v is. V just represents the antiderivative of dv, which we already know is just e to the x. So once I have these 4 pieces of information, I'm ready to rewrite my function. So this antiderivative of x e to the x dx can be rewritten as u times v are these two. So I get x times e to the x minus, now before I move on to the next part, you'll notice that, hey, well that's the same thing as what I started with. Isn't that a problem? It's not a problem because look, notice what's missing. I don't have to integrate this anymore. This piece is already integrated. No integration necessary for that first piece. The second piece, I still need to integrate. But the second piece is doing v times du. So e to the x times du, or 1 dx, which is just dx. So I took this starting integral that had a product of 2 functions. I chose a differentiable function, I chose an integrable function, and I used integration by parts to rewrite it. So now I'm done rewriting it. What do I notice? Take a look at my new integral. Once again, this one's already integrated. I don't need to worry about that one anymore. So take a look at the piece that I still need to integrate. Is that simpler than what I started with? Absolutely. It's simple enough to where now this is possible. I know how to find the antiderivative of this, and I get x times e to the x minus the antiderivative of e to the x is just e to the x. And since it's indefinite, make sure you add the plus c at the end. So even though it looks like it's getting more complicated, if you choose your u and your dv correctly, you'll end up with an integral that you can actually find the antiderivative of. Now, this wouldn't have been the case if we had chose these the opposite way. If I had switched this around and chosen e to the x as my differentiable function and x as my integrable function, what would have happened? I would have ended up with a more complicated integral when I was done with it. So your choice of u and v, or u and dv, very much matters. So let's look at some guidelines of how you can choose u and dv. In general, when you're working with an exponential function, we want to choose that as my integrable function. Why? Because the derivative and the antiderivative are very, very similar. They're pretty much the same thing. The only thing that's going to be different is maybe constants, depending if you have a constant multiple in the exponent or not. But in general, we want to choose the exponential functions as our integrable functions. With our differentiable functions, if you ever end up with a logarithm function, or just natural log of x, we actually have to choose this as my differentiable function. Why? Because I don't have an antiderivative rule for natural log of x. So this one has to be chosen as the differentiable function. And then the other type of function that we, of course, know how to work with are power functions or polynomials. I'll put that in parentheses, polynomials. If you're working with a polynomial, you can take the derivative of it or you can take the antiderivative of it. But usually we want to choose it to be the differentiable. Why? Because the function gets more simple if we choose it as the differentiable function. So those are just some good guidelines of how to pick your u and your dv. But next we need to talk about how does integration by parts work if I have bounds, if I'm working with a definite integral. Well, once again, all integration by parts is it's a way to rewrite my integral in a way that's more approachable. Bounds really don't complicate it too much. If your integral is bounded from a to b, then the new integral that's created will also be bounded from a to b. But what do I do with this piece that's already integrated? Well, the way that works is you just act like it's already integrated, and all that's left to do is to evaluate it from a to b. So you treat that piece as if you've already found the antiderivative, but you still need to plug in the upper bound, plug in the lower bound, and subtract them. So that's all that bounds will do to integration by parts. Well, last we need to talk about situations where you may need to use this multiple times. Consider this function, x squared e to the x dx. Like we already said, we want to choose my exponential function as my integrable function, and I'm working with a power function for my other one, so this one I want to choose as my u function. But notice what happens when I actually use integration by parts. I get x squared e to the x minus this integral of 2x e to the x dx. Has my integral gotten simpler? Is this new integral more simple than what I had before? Once again, this first piece is done. I don't have to worry about integrating it, so it's okay that it's still x squared e to the x. But is my new integral simpler than what I started with? Well, absolutely, because here I have a power of 2, and here I don't have a power of 2. I just have a nice linear function, 2x. So it did get simpler, but how do I integrate something like this? How do I find the antiderivative of this? I have to use integration by parts again. So there may be cases where you have to do this multiple times in order to get down to a final answer, in order for you to be done finding antiderivatives. But what's nice is I actually have like a hack for how to do this in a more simple way than trying to do it all by hand. And this is called tabular integration by parts. So let's say you've got an integral of two functions, f of x, g of x, and you're going to choose f as your differentiable function and g as your integrable function. So once you decide what your differentiable function and integrable function are, you can actually make a table, which is why it's called tabular integration by parts. So f is my differentiable function and g of x is my integral function. So what I'm going to do, if I start with the left side, what I'm going to do is I'm just going to take the derivative of this function over and over and over again until I reach 0. Because most of the time with this tabular integration by parts, you're choosing u as a power function that'll eventually get all the way to 0 if you take the derivative long enough. But then g of x, if you're taking the derivative of this function over and over again, with g of x, I'm just going to take the antiderivative over and over again. Right? Antiderivative, I get capital G of x. I don't really have a good notation for multiple antiderivatives, so maybe I'll just put a little 2 up in the corner, say, hey, that's my second antiderivative. Then I'll take my third antiderivative. Where do I stop? I stop at the same row where I get 0 for my derivative of my differentiable function. So that's where I'll stop. Once I have my table filled out, to complete the process, I'm actually going to multiply, starting with my original differentiable function, I'm going to multiply in a diagonal way. So I don't multiply straight across, I multiply kind of diagonal downwards. And I'm going to do this all the way down the table. So I'm going to multiply those things, and then I'm actually going to alternate whether the product is positive or negative. The first one I want it to be positive, the second I want it to be negative, positive, negative, positive, and so on and so forth. So what will that look like when I'm done? My first term will be f of x and the antiderivative of g of x. Notice how I left it positive. Why? Because the first one is positive. The second one is negative, so I'll go ahead and start by putting a little negative symbol. And with this one, I'm going to do the derivative of f of x multiplied by the second antiderivative of g of x. My third one is going to be positive, and this one's the second derivative of f, and the third antiderivative of g. And I'm just going to keep going, so on and so forth, until I reach that very last term. And then that will be your antiderivative. So not too complicated. It's long. It'll be long and not very fun to do, but if I have this method of tabular integration by parts, it makes it a lot easier than trying to just do it all by hand. We'll go through one of these in the examples video. We'll also go through an example of a definite integral just to help you out with that. But go ahead and get started on the homework, see what you can do, and then tune into the examples video once you get stuck. Good luck, and I'll see you in the next video.